Welcome and thank you for attending this session. The intent of the session is to get a good idea of how to go about migrating a CUDA application to data parallel C++, and also to know what are the best known practices that would help you to make this process more efficient. So my name is Edward Mascarenhas. Besides myself, Sony Gogar, we both work at Intel. Sunny will be doing the presenting, part of the presentation, and also doing the demo. Sunny, are you there? Okay, I hope he is there.
Yes.
We'll,
Yes.
okay, great. All right, that's good check to make sure you're there. All right, let's move on. All right, so here's the agenda and the topics we will cover. We'll start with a brief one slide overview of oneAPI just to set the context for people who may not have attended the other parts of this workshop, and also for folks who might see the recording later. Then we will describe the data parallel C++ compatibility tool workflow that is typically used to migrate CUDA applications. We'll also use a simple vector add application to demo the migration output and highlight the changes in the migrated code. And this will provide a good basis for the demos that are following, where we'll have more complex examples, migrating a single CUDA file project, as well as migrating multi-CUDA file projects. So in terms of examples, we're going to use one of the Rodinia benchmark suite called Needleman-Wunsch, which is a bioinformatics code for sequence alignment. And then the second one is a hydrodynamics code called HydroC, which is the multi-CUDA file project. Both of these are open source codes, so they are available off the web. And then after the demo, we will discuss best known methods that are typically adopted in the migration process that we've found in our own work while doing migrations of these, as well as other larger codes. And then finally, we'll talk about the use of integrated development environments like Eclipse and Visual Studio, and summarize at the end with some key takeaways. All right, so why are we here? Why oneAPI and data parallel C++? So oneAPI is Intel's solution to deliver an unified software development environment across CPUs and accelerator architectures like GPUs, FPGAs, and AI accelerators. So it has two components, the oneAPI industry initiative and a implementation of the oneAPI Intel product. The intent of the oneAPI is to provide a common developer experience across all of these architectures, scalar, vector, matrix, and spatial, that generally map into the CPU, GPU, specialized AI accelerators, and FPGAs. So we have an explicit programming language to support this unification, which is data parallel C++. And oneAPI software also includes other compilers, tools, libraries for expressing parallelism. These are packaged as toolkits, and I'll provide more information towards the end about how to access these toolkits. Data parallel C++, of course, provides direct programming in standard C++, which gives a huge amount of flexibility in programming and also is able to get native high-level language performance. It's based on industry standards and open specifications of C++, SYCL from the Kronos group, and LLVM, which is a compiler technology that's been developed in the community. So this basis of using open specifications and standards promotes cross-vendor collaboration and community contribution to the tools and to the library development. So this is showing a flow of how typically we do migration of CUDA code at a very high level. So Data Parallel C++ compatibility tool is a tool that can be used to migrate programs written in CUDA. And the idea is to minimize the code migration time and the effort. The tool is available as part of the oneAPI core toolkit. The process usually involves some preparatory work to identify the source files that are written in CUDA. Then using a tool called intercept build, which is part of the core toolkit. And with that, we create a compilation database that captures all the compilation commands to migrate the CUDA files, including various macro definitions, headers, etc. Once that is done, then the tool itself is used to transform the code, the CUDA files, to DPC++, and there's a DPCT program that does that. Now, non-CUDA files are typically migrated without any changes. We can expect on average up to 80 to 90% of the CUDA code to be migrated automatically. But this amount of migration is dependent on the type of CUDA features, API calls, etc. that are used, and it can be less than that. So what that means is there has to be some human intervention and some plumbing work that has to be done to make sure that the code that got migrated is correct, functional, and definitely we will need to do some tuning to get to the best performance. Now the migration with the DPCT program is to be done only once, and once it's correct, functional, then you can put it under source code control. So let's now use this vector add example to demonstrate or show the kind of changes that occur typically with this tool. So this is a side-by-side comparison of the vector add example, which you can get from here at the bottom of the screen. So the idea is to go through this example, and this should basic framework should help us to understand more complex examples that are coming next. So we have the CUDA side here with the CUDA header files. The equivalent or similar DPC++ header files are cl_sickle.hpp and dpct.hpp. Now the dpct.hpp contains some helper definitions that help with the migration. We're using a vector sizes of 256 here. So basically we are taking two vectors A and B and putting the result in vector C. The next part here is the kernel itself, which we are wanting to offload to the GPU or some other accelerator device and do the computation. So here you can see that the kernel, we have three vectors, A, B, and C passed in as pointers. There is this concept of a ND item class, which is used to specify work items. This is a sickle class. And the key thing to notice, of course, is that on the CUDA side, we use the thread ID to identify the work elements, whereas on the DPC++ side, we use the ND item and use the get local ID function to get to address the specific work items. So in this case, we're not showing any error handling, as you notice, but typically in Data Barrel C++, we use the try and exception blocks, and it's possible to put the bulk of the code in the try portion of the block and catch exceptions asynchronously in the exception part of the code. In the main section here, we are showing memory allocation for those three vectors. But before that, here we compute the current device. Now, Data Parallel C++ does provide options to select the particular device. There are functions available. So you can pick the default device, or you can pick the host device, the CPU device, and so on. And also we have a queue to which we will be submitting the work that is to be done, basically the kernel that we want to be computed. The CUDA malloc on this side, which is basically allocating memory, is migrated to the malloc device, which what it does is it allocates memory on the device, on the GPU device, or whatever device is selected over here. So next, we show the code that submits the vector add kernel to the command queue for execution. The command group handler, CGH, encompasses the data, the synchronization, and the computation that is submitted to the queue. The parallel for is called for a number of global elements, in this case 256, and the number of work items in each work group, which is, in this case, again, it's 256. This last part is where it calls the kernel. Sometimes the code is more verbose in this case because the tool tries to be general and tries to do the migration in a very generic way. There is a possibility of hand coding and improving this code. For example, we don't need to use a three-dimensional ND item here. We could use a single-dimensional ND item. So next, once this computation is over, and the computation will wait until this is over to get to the next code here, and that's kind of built in as part of the language. What we do here is then we have the result. We copy back the C array back into the result. And again, we wait for this copying to be over. So this is the migration of the CUDA memcopy in CUDA. Finally, we free all the arrays once we have the results, and then we print the results out. Now you'll notice that this part of the code is kind of migrated as is. There's no change. And that's typically for the bulk of the code, which doesn't use CUDA. This is what it will be. All right, so I think we'll move on to the demo portion, and then and Sunny, would you like to take it over?
Sure, thank you, Edward. Can you flip the slides for me? Yeah, thank you so much. As Edward mentioned before, right, the typical migration flow for any application using the make or CMake or type of build environments, right? You will start with preparation to migrate, which is usually done with the help of intercept build command. So as the name suggests, what intercept build does is intercepts the build process and logs important information about the building or the compilation, which is if there are any compiler flags which needs to be passed to the code, which enables or disables some portion of the code. If there are any include headers which need to be specified for compilation of project. So all these information and plenty of other information is captured using the make or CMake make you were running, and it's logged to a compilation database. Now, compilation database is a JSON file which we are going to take a look when we look at the demos, all right? But it's a JSON file which captures this information and stores it. Now, this compilation database is then used in the migration phase when we actually run the migration utility or the tool DPCT. So DPCT runs, and it will create the data parallel C++ files and store it in an output directory, and with the DPC++ sources, and also additional messages, warnings, which can assist developers to the complete the sources and for functionality and correctness. So that is usually done in the verify and manually edit process. There is a full-fledged diagnostics reference guide which is provided as part of the compatibility tool, which can assist developers to complete this final stage even better. Next slide, please. So now I'm going to cover two demos. One is focusing only on a migration of a single source file. This is done so that we can focus more on the aspects of the compatibility tool rather than the application or the CUDA sources itself. So for this process, I'm going to use some Jupyter notebooks for demonstration purposes. They are not a must for running or using compatibility tool. It's just used for demonstration, and you can complete most of the steps using command line as well. So let me just go ahead and share my screen instead, Edward. All right, so this is the first demo. We're going to look at Needleman-Wunsch. It's an application from Rodinia Benchmark Suite. It's a single CUDA source file application which suits the bill here. We can demonstrate how compatibility tool can be used. So what users are going to learn in this demo is how to use the intercept build utility or the script. Then how to use the DPCT command to migrate the code. And then we will discuss some of the aspects of the review process, like what are the things developers will need to keep in mind when the migration has complete and now they are ready to work compilation. So just bear with me. I have okay, this came down now. So as the Okay, so as the command says, we are going to run intercept build. It is simple enough. You will be using the basic make or make commands, and you have to prepend them prepend that using intercept build. So it's as simple as that. You run intercept build with the make. So what happens is when this done, right, you are not compiling your code with the NVCC compiler. What it does is it sort of just captures the compilation command and stores them in this compilation database, which is called compile commands.json. So let's take a look at how this compilation database looks. So if you see here, the compilation database is simple enough. It captures the command which is used to compile the code, which is NVCC with the additional include files. There are some compile variables like CUDA CC here, and then it also includes the file name itself, which is being migrated or which needs to be migrated. It has other useful information like directory and the file structure as well. So in this case, because it was a single source file project, right, we got only one entry. If the application itself has many files, you will find like one entry for each of the source files. Now, this is useful information for DPCT tool because when it's migrating file by file, it has to know how the file needs to be migrated. Because a lot of times you would migrate the entire project, but DPCT also allows to migrate one file at a time. And as a result, a lot of this information is duplicated and provided per file base, so that that can be achieved. So we generated the compilation database, and now the next step, what we need to do is run the DPCT tool itself. So ideally, if you are trying to migrate the entire project, once you have the compilation database, you don't need to provide anything else. Just call DPCT with -p and the location or the directory of your compilation database. So in this case, it's provided with the help of a -p variable. If you want to structure your generated output, or you want to provide a subset of your root directory where the CUDA sources are present, right? Then you can also provide that information additionally or optionally with the help of --in root, which basically specifies the root or input root directory. And you can also specify --out root, which tells the DPCT to generate and to save your files in a particular or specific directory. In our case, we'll just let the default options kick in and see what happens. So as you can see here, the directory DPCT output was created, and it's been used as out root. What you would see as the output of DPCT command is all the warnings which are seen by DPCT, and they are left as a log for the developers to complete the migration. Now, in this case, it's just like maybe a couple of warnings, but when you are migrating like a large project, you might have hundreds of warnings related to this. But you don't have to capture this output. Most of the warnings are actually also logged in each individual source file, so that once your migration is complete, you can do the remaining plumbing work one file at a time. You don't have to worry about this text message which is output here. We will go on and understand what this warning message is later on, but for now, just understand that it's been logged here and also in the files. So the migration is complete. In this case, there were only a couple of files. There was a needle.dpcpp, which was a driver project for CUDA. And then there was a kernel file, which is migrated as it is a needle_kernel.dpcp. I mean, you can review the files using Jupyter Notebook or any choice of editor. I would go with the terminal and VI editor for now to discuss further. So this is the same directory where we generated the output. As you see, the DPCT output folder was created. Let me open up first the kernel files. Needle_kernel.dpcp. Okay, so here what you see. So here what you see is on the left-hand side, what you have is the CUDA project, the CUDA kernel as it is. And on the right-hand side, what you see is a migrated SYCL kernel, okay? So if we look at the first line, we see that there are some a couple of additional variables added here. So for example, you'll see the temp and reference, right, which are the shared local memory buffers. They were not in the CUDA portion, but if you see the shared and the temp and ref are actually shared memory buffers, which are created in the CUDA kernel itself. However, in SYCL, your buffers are created before invoking or before the kernel definition, and a reference to that or accessor to that is passed in the kernel. So that's why you'd see temp and ref here for the shared local memory. For remaining portion of the kernel, there is not a lot of difference. The code is as it is, you would notice that the sync threads is been migrated to appropriate barrier, which is the SYCL barriers. So that the synchronization itself carries over as it is. The other portions like the loops and all, they still remain same. There is no difference at all. So if you see the kernel body itself doesn't change a lot. So your kernel is migrated as it is with some of the requirement, with some of the things which SYCL needs are migrated as it is. If you see other kernel, it's migrated as well. The needle CUDA shared too. And the similar aspects are maintained here. The block indexes, the thread indexes are migrated to work item indexes in SYCL and so on. Okay. Uh, let us look at the driver function for now. So if you see the project which is not CUDA, or the source lines which are not CUDA specific, they are migrated as it is. Here on the left hand side, what you see is the CUDA file, and on the right hand side is your data parallel C++ driver file here. If you see the most of the code is migrated as it is, which is not CUDA specific. And once we start reaching a portion where you are invoking the kernel, right? For example, in line 176 onwards, you'll see that appropriate SYCL references are made. So as I mentioned earlier, right? You're in SYCL, your local memory buffers are created before your before parallel 4. So this is where this is happening. Your local memory buffers are being created, and they are provided a range of values. Then you have your parallel 4, which takes care of the ND range here, which by default migrates to, everything migrates to 3D ND range. But if you are using a single dimensional range, then you can hand edit this code to suit your needs. But this should not affect any performance or anything. It's just that because CUDA uses by default three-dimensional work group launches or three-dimensional CUDA thread blocks, it's been migrated as it is to 3D ND range. One thing what you will notice is that in the original CUDA file, right, or the CUDA sources, the block size was used as a preprocessor directive to set the size of your ranges when it comes to the size of your SLM buffers. So in this case, because the DPCT tool, it derived the value of block size to be 16, you see, you will there are the values 17 and 16 are used as hard-coded values here, as seen by the compatibility tool. But in case, for example, you want to change your block size to something else, 32, then this program will be incorrect. This source file would be incorrect. So you will want to make sure that before you try compiling your code, edit these values. And the compatibility tool itself, right? It has left you warnings on what needs to be done. So the 17 will be replaced by block size +1. And in this case, the 16s will be replaced by block size, which will be functionally correct thing to do. Also, if you see, DPCT tool left a DPCT diagnostic message here. So DPCT diagnostic messages will be logged in every migrated file. We maintain a keyword, which is basically DPCT10, which is then followed by a particular number of diagnostic messages starting from DPCT100 to some value like 75 or something. There is a big reference guide which shows you details about each diagnostic message, what it means, and how to fix it for the developers to take care. Now, In this case, what my diagnostic message is telling is that we use the work group size, whatever was used in CUDA, right? But it's developers' responsibility to make sure that the work group sizes or the CUDA thread block size which was used, it suits, or it is a legal value for the device you are intending to run. For example, if you intend to run this code, a migrated code on a Intel Gen 9 graphics card, which has a limit of 256 workgroup size, then in that case, the size will be, that will need to be taken care of before you try to compile and run your program. All right, so let's get back to the Jupyter Notebook now. Since we covered the kernel body itself, we covered how the shared memory local memory declarations look like. We saw the synchronization primitives when we saw the migration of sync threads to the barriers. We looked how the host and device buffers looked, the parallel for and the lambda expression. And we also saw the kernel invocation, which was used by migration tool. So if you would like to also see and verify the diagnostic messages, one of the things which I do is after migration, do a grep of DPCT10 to each of the files. So if you run this grep, right, what it's showing is, okay, I am having a lag, I'm sorry. Okay, so DPCT 1049, the same warning message what we saw, and how to tackle that and so on. So in this case, it was simple enough because you had single source file. But when you have lots of file, it is useful to grep and understand each of the diagnostic messages. If I have been talking about diagnostic messages, just take a look of how the diagnostic message reference guide looks like. So it has the ID of the message itself, what the message is, what it means to the programmer in detail, and compatibility tool reference guide also provides how to fix it, some suggestions on how to fix it as well. So there is this detailed help. You can definitely take a look once you try out the compatibility tool. Okay, I'm trying to. Okay, the compatibility tool also has some additional options which you can provide. We already discussed the in route and out route, which helps you provide the directory path for the input source tree and also the output route. There are other useful command line options as well. One of them useful I've seen is the USM level. So compatibility tool by default, it will generate all the migrated source files with the use of USM API. Now, a USM API was not part of the SYCL base specification, but if you see the SYCL 2020, USM is now the default part of the SYCL specification. It's no longer just an Intel extension. It is part of the specification. So you can leave the code with as it is by letting the DPCT generate a code with USM, or if you intend to use the generic SYCL buffer approach, then in that case, you can set this value to none. And in that case, the DPCT will generate code without USM API. CUDA include path is another variable I've used, and it is useful. It's in scenarios where your CUDA header files are installed in the non-default directory. So CUDA uses this /usr local CUDA as the default directory of CUDA installation. But if your environment has any other directory, custom directory, then you need to provide this CUDA include path with your DPCT command, so that the compatibility tool can migrate the files correctly. There is this another variable, use extra arg. So in general, when you're using compilation database, most of the arguments are already captured. But you may see a situation where one or two include files are missing or include paths are missing. Then in that case, those can be provided as an extra argument to the compatibility tool or the DPCT. Also, if you are trying to use compatibility tool without the compilation database, now this could happen if your CUDA project was not using make environment, right? You were compiling the code using command line NVCC. Then in that case, this extra arc can be useful to provide the extra information like the include paths and so on as well to allow your migration without the compilation database. There are a lot of other options, useful options, which can show you probably the statistics, the C++ standard format, which needs to be used. Like by default, CSTAT 17 is used. You can change to as per your needs. There are other things like, do you want to format your DPCT generated code? If yes, what format? Google, CLang, etc. So these kind of other options are available, which can be seen with the DPCT-help. All right. So this concludes our first simple CUDA source migration, which was Noodleman Bunch. Now let's use what we learned and try to apply this to an application which has more than one CUDA source file. So for this second demo, what I'm going to use is a Hydro-C application, which is a hydrodynamics application. It's one of the applications which you can find online on GitHub. The links are attached here. It's one of the projects we work in collaboration with CEA, and I've used this with their permission to show the migration utility. Now, as we learned from the first project, right, we use the same steps: intercept, build, DPCT, and then we review diagnostic messages to complete the migration. As a prerequisite for this project and this demonstration, what I've done is I've already cloned the Hydro project as it is. And because this Hydro project has a lot of variations of the variations in terms of which language to be, the example is shown in multiple languages like OpenMP, MPI, CUDA, and so on. What we are interested right now is in one project which is using MPI and CUDA. So that's why I'm going to the specific directory. And there is this additional step use, which is written in the README file of the project of creating this symbolic link for a make file. So this has already been done, and it's part of the build preparation environment, which I've been talking about, like the first step. So just give you a hint about how the source files look like. Not the source files, I mean the content of the project looks like. So there are about 14 CUDA files in this project, and there are other C-based, which using MPI plus the C source lines. About 2,000 plus lines of CUDA code, which will be migrated to data parallel C++. And it's a good enough example to show a demonstration where you are migrating more than a few lines of code. So first step is we prepare the build environment. One of the things for the preparation of the build environment is to make sure that you are taking care of all the MPI. You're taking care of the include paths and so on, which are used in the make file itself. So one of the things which I had to edit as part of the build or preparation phase is to make sure that the default default MPI path has been corrected. So this project was using the MPI paths from a different MPI distribution, right? So in this case, because my system has access to Intel MPI, what I'm doing is I'm just modifying this MPI root to IMPI route and fixing that path. So as the next step, now once we have edited that make file, I will go ahead and run the intercept build make command. So as seen here, there's a lot of messages generated, but and these are logged and captured to our compilation database. Because this compilation database has a lot of files, I'm not going to open the compilation database, but it does capture all the information and logs there. Now the compilation database is generated. We are going to say use that to migrate our files with DPCT. What I'm doing here as an additional step for demonstration is I'm passing another flag, keep original code. So what this flag does is it will, as the name suggests, when it's migrated the code, right? It leaves the CUDA code itself inlined as well, so that when you are reviewing the code and fixing the migrated code, you can have a good view of your original CUDA code and then what changed and how does the migration code looks like. This is often a useful exercise when you're dealing with a large project where you will have to spend a little bit time doing the manual reviewing process and the manual editing process. So let's go ahead and run the migration project itself. So as we can see here, lots of diagnostic messages are generated. Oh, just one second. Yeah, so lots of migration text is generated here as part of the compatibility tool migration process. But all these messages are also logged in individual source files. So we need not worry about it. Okay, so let's look at how many files did we migrate. So what I'm going to do is just show the directory structure now. If you see the 14 CUDA files which were in the Hydro project were migrated to respective data parallel C++ file with an extension .dp.cpp. What we are going to do as part of our remaining demonstration is to understand the diagnostic messages. So what I have done here is captured all the different types of diagnostic messages which I've seen for this Hydro C project. Right. So this is basically, this text is taken from the reference guide as it is to so that we can have easy review here itself in the Jupyter notebook. So first what I'm going to do is look at the first DPCT 1000 message or DPCT 100 message and see what it tries to tell us. So if you look here, right, on line 102, we see DPCT 100 error handling if statement was detected but could not be rewritten. Now, what it tries to tell us is that you had this status not equal to 0, right? So CUDA uses, so DPCT original, which basically has the original CUDA code. It says is that status is equal to CUDA set device. Now, SYCL does not use these sorts of status messages or error handling itself in data parallel C++ or SYCL, right? So as a developer, if you had this sort of logic and decision making which based on the statuses, right, then you will have to review this code, because if you see here, we are actually using a non-zero value here, and we are not going to stop here at all. So your error checking which were supposed to happen in the CUDA, it is not migrated as is in this code. So you will have to look at or address all these occurrences and fix your code as needed to be functionally correct. And that's because SYCL actually uses error codes. SYCL uses exceptions, asynchronous exception handling, and not error codes in the way CUDA was using. If you look at the second, DPCT 1003 message, right? It is also related to error handling. As I mentioned before, SYCL uses asynchronous exception handling, and you can use sort of try-catch blocks and different ways to address your exceptions. All right. What the DPCT migration tool does is it replaces. So if you look here, right, 210 line status is equal to CUDA malloc, and we are trying to get that. Now, what DPCT does is replaces this code with a *0, right? What *0 does is it assumes that your code returns a positive status, that is your CUDA malloc finished. In case in your SYCL application, the CUDA or this malloc device, it fails, you will see an exception. It's not that we are not handling, it's not that we are not going to catch our errors. It's just that the migration tool assumes that things are correct. Now, if you want like to address these exceptions, then you will need a specific try-catch block, which will, or some sort of try-catch block will need to handle these exceptions in such scenarios. So this is something developers will have to review and fix after the migration is completed. Let's look at maybe one more diagnostic messages, or maybe a couple of more diagnostic messages. Yeah, DPCT 1005. Okay, the device version is different. You need to rewrite this. Now, what it tries to tell us is that SYCL doesn't have APIs specific to something which was equivalent to CUDA compute capabilities, right? So if you are making decisions with device property.get major version as happening here, right? This will need to be rewritten. That's because we don't have a one-on-one equivalent API in SYCL. There are other APIs which could be used for making decisions with respect to your device properties, but these are not completely like one-on-one equivalent. So that's why occurrences like this will be marked by a compatibility tool for something that the developer will need to address and fix as needed. DPCT 1009. So what we are doing is another error or another message related to the exception handling, which says that the CUDA was trying to understand the error and insert some supporting string with respect to that. Now, DPCT again, since uses or the SYCL by itself uses exception to handle errors, right? So it's not migrated correctly. Instead, what's done is that the CUDA get error string, which was in the original code, it's being commented out here. So occurrences like this of DPCT 1009 will need to be rewritten. So you will see a common pattern that a lot of things related to error code handling, which was done in a lot of CUDA programs. It's something where your attention will be required because of the difference in the way errors are handled in both CUDA and data parallel C++ or SYCL in general. So most of these things will be taken care of and worked on after your migration is done. And let's look at the last last message here. This again is with respect to this device error says that CUDA success is not available in SYCL. There's no API for that, and hence the status is being modified to be some manager instant here, and the status is being compared as it is. So your check error, which is check error CUDA set device, compatibility tool could not do anything with respect to this. So if you want specific logic to be embedded in your code, then in that case, that will be, we will need to address that and fix before you try to compile and run your application. As I mentioned before, diagnostic reference is a good place to start once you have your migration done. Grep for the DPCT command file by file, and refer to this this reference guide, which has information about most of the diagnostic messages we saw, and can be reviewed. And at the same time, compatibility tool team will try to provide a useful hint on how to fix your error message or fix your warning message, which you are seeing with compatibility tool. All right. Edward, can you share again and share the presentation?
Yep, sure.
There's a question in chat. It says the for loop on the left is more succinct and readable compared to the migrated side. Why is that?
Was this respect to the Needleman-Wunsch code?
I would think so, based on the time that it was posted, Sunny.
Okay, and let me see. Let me first get to see which for loop was. Was it related to the parallel for? Oh yeah. So yes, I would agree that the code generated by compatibility tool is it can be verbose sometimes. And the reason I would mention is before is also that the compatibility tool tries to generate a generic code, right? So for example, things like for things like ranges, right? Ranges of your CUDA thread blocks. Now, SYCL or the compatibility tool tries to generate most generic message, right? It will try to say each buffer, what type it is, read, write, what kind of accessor it is using, and so on. This tool is also maturing as we as we are moving along, right? So there are new SYCL APIs which kind of reduce the verbosity of SYCL itself. And as and when that happens, the compatibility tool will try to generate more succinct code as well. Yes, it's a known problem that SYCL can be a little bit verbose by itself, the old standards. But with SYCL 2020, right, there are a lot of new features being added, which makes the declaration of accessors, ranges, and so on pretty shorter, small. So if you look at the code samples which are being provided with oneAPI toolkits, right? We are taking care of, or we are including all the new features in there as part of the SYCL. So those can be referred and used in your migrated code, or if a couple of releases later, if the migration tool itself catches those changes, then it might include include those features and generate a more succinct code for you. I hope that answers your question to some extent. All right. So what we found out was that we can use this compatibility tool, which can reduce the time a developer would require to migrate the code from CUDA to data parallel C++. But there could be some scenario where your project is just too big, so that you just cannot generate each file, like you cannot generate every file together. So what we do in such scenarios is migrate file one by one. This has worked in cases where if your compatibility tool just gives you error on a specific file, right? Then in that case, migrating all your remaining files, and now that one file which is creating a problem, you can actually look at the API which is causing that issue, comment out the issue, try to comment out that in the CUDA source file, and try to migrate one by one, or that individual file itself. So this has worked as well. One BKM would be also to always make sure that you use make clean before you're running intercept build command, because a lot of times if your make is skipped because your object files were already present there, then in that case intercept build just fails to intercepts the commands, the compilation commands. So that is one thing. Another hint I would have is, like, in some scenarios, if you have dependencies and your make that itself doesn't finish right, then a running intercept build with make and a -i flag, which basically tells the make to continue even if it sees errors, right? Ignore the errors. So in that case, what happens is that your compilation commands are still captured and intercepted by the intercept build, and they are logged into the compilation database. So if you are seeing that your make itself is failing for some reason, then -i is sometimes useful to complete your intercept build command, or have the compilation database created. All right. Next slide, please. So now I will hand it over again back to Edward, so that he can cover how to use compatibility tool or with the IDEs using some of the plugins. Thank you, Edward.
Yep. Thanks, Sunny. So in the next couple of slides, I'll introduce the use of the integrated development environments, Eclipse and Visual Studio, how they can be used with the compatibility tool. So our developers have spent some time integrating the compatibility tool with these IDEs. And it's useful for those folks who are familiar with these IDEs, and it can further improve your productivity. But these are not essential. Don't have to use, as Sunny demonstrated earlier, you can just do command line and use the compatibility tool. The example that is being used here is another one from the Rodinia suite. It's called Gaussian, which is used to solve systems of equations. And the reason why we've been using Rodinia is because it does give a large number of examples, and they have examples, the same code pretty much implemented in oneAPI, CUDA, and there are even SYCL versions available now on the web. So that's it was meant to be a method of demonstrating heterogeneity. So that's part of the reason we are using the Rodinia suite. Okay, so this is showing the Eclipse IDE with the plugin installed. We do give on our website information on how to incorporate the Eclipse, the Data Parallel C++ compatibility tool plugin into Eclipse. And when you do that, you'll see this additional Intel option over here. Now, the way to do this is to click the project on this one, and then there will be an option called Migrate Project to Data Parallel C++. Once that is done, this particular file, gaussian.dp.cpp in this case, will show up. So basically, under the covers, the project is migrating the gaussian.cu file into the gaussian.dp.cpp. So there is at the bottom this Intel DPC++ compatibility tool panel, and a list of warning messages appear indicating that the migrated code contains something that the user should pay attention to, which is normal, as we've been mentioning it all along. And it means, of course, that the tool could not migrate all of the CUDA code into DPC++. So if you do click, of course, this is a screenshot, but if you do click one of these items here, then it will jump to that particular part of the code where where it's trying to draw attention for the developer to go and see how the migration was done, what the change was, and what changes might be needed. And also, if you click on the help button here, then the diagnostic messages that Sunny was talking about earlier on the web page, that exact same diagnostic message for DPCT 1003 will come up, which will give some idea of how to fix the issue. This next slide is about Visual Studio 2019. And it's the same example, and there are many similarities between how the menus appear in both these cases, but they are slightly different. So here the menu item names for compatibility tool are similar. One major difference is when you choose the CUDA sample to be migrated, you would select the VCX proj file of the CUDA project. And other workflows are almost the same. There are differences, as you can see, but there are similarities. There are these items in the panel at the bottom for the compatibility tool, and we still have the help sections here to jump to the particular diagnostic message. Okay, so the key takeaways from this are that oneAPI delivers a unified programming model to simplify development across all of these diverse architectures that as developers and programmers we need to handle in today's world. Intel DPC++ compatibility assists developers in migrating code written in CUDA to data parallel C++. The intent is to increase the developer productivity and reduce the time it takes to take existing CUDA code and migrate it to use DPC++. And also want to emphasize that DPC++ is an open specification. The specs are available. SYCL itself is an open specification. There's a lot of information on www.oneapi.com. It's architecture neutral language for expressing parallelism, and it is based on industry standards. Finally, as other folks you may have heard already, so if you're ready to try oneAPI, we have Intel Dev Cloud, where you can go and try out codes. You can identify potential workloads from your existing work. You do have to download DPCT from the core toolkit. There is a website available to do that. If you just Google search, you should be able to find it. And typically you would migrate the code, run this tool on your premise, on your own computer, if applicable. And then you can test and tune and optimize this code on the Intel Dev Cloud. All right, so this is a sandbox environment that we provide. It has all the software loaded, installed already. It also has hardware like the Gen 9 Intel integrated graphics already there. And we keep adding the latest Intel GPU hardware on the Dev Cloud as it becomes available. So this is the link to the Dev Cloud.
That's from my side.